Hello and welcome back to Organic Chemistry, Semester 1. We are in the middle of Chapter 7. Now, in the third edition, where we're about to talk about the E2 reaction, this is all discussed in Chapter 7, 7.6, which is the number that you see up here. Now, if you're using the second edition of the book, the material is the same, it's just that it's moved into Chapter 8. I believe it starts on section 8.7, but just double check. Basically, Chapters 7 and 8 get mixed around a little bit from the second to the third edition. So just know, like, when you're looking for the E2 stuff, that's actually going to be in the chapter 8 section of that book here. So let me know if you have any questions and I'll make sure to point you in the right direction for that. But okay, so we're talking about E2 reactions. Now, E2 reactions, that's a type of elimination reaction. We mentioned that back a couple lectures ago, what an elimination looks like. Now we're going to actually look at what the mechanism is like. So we mentioned that alkyl halides can undergo an elimination reaction when they're treated with a strong base. And so we'll look at different strong bases here in just a little bit. But what happens is what we call a beta elimination or a 1-2 elimination. Basically, remember your halogen is bonded to the alpha carbon. Then its neighbor is the beta carbon. A hydrogen is going to be deprotonated from the beta carbon. So you basically have to have a beta hydrogen that can be deprotonated, and you're treated with a base, and you end up with an alkene. So it's like you form a new pi bond here. And then just kind of bookkeeping here, of course, the base becomes the conjugate acid, and then the halogen leaves as a halide. So you're left over with the halide that left. Okay, so here is the mechanism, okay? This is the E2 elimination mechanism. And the key is you need to have a strong base, and a strong base will have a concerted mechanism. Remember, that means that all of these steps happen at the same time, so simultaneously. And let's follow along what happens with the electrons. So starting from the base, right, the base has a lone pair. It's going to deprotonate the beta carbon. So it's going to do a proton transfer, basically steal this proton from the beta carbon. Now, when that happens, rather than like in a normal proton transfer, where this carbon would be left with the lone pair, this lone pair is actually going to form a new pi bond between the alpha and the beta carbons. Now, that would break the octet rule here for the neighboring carbon, but at the exact same time, the halogen that is on the alpha carbon is going to leave as a halide. So it's three different arrows. One is the proton transfer, which involves the base picking up the proton, and then the carbon hydrogen bond from the beta carbon forming a new pi bond. And the third arrow is the loss of the leaving group. So this alpha carbon to halogen bond is going to go as a lone pair on the halogen. Okay, so why do we call it E2? Well, if you were paying to SN2, you notice that was a bimolecular nucleophilic substitution. Well, E2 is bimolecular for the same reason, bimolecular elimination, because in the rate limiting step, there's two different molecules involved in this rate limiting step. So it's dependent on the collision of those two. So recall from our studies of kinetics, that means that it's the rate of the reaction is going to be dependent on both the concentration of the base and of the alkyl halide, like so. So that's why we call it bimolecular elimination or E2 elimination. Yeah, and that's basically the big similarity here for E2 elimination and SN2 substitution. Now there's several differences, right? I mean, one is that with substitution, you get a new carbon X bond, whereas here with the elimination, we're just forming a new carbon-carbon pi bond. So you can kind of like process that as you're thinking about it. Okay, so first off, let's talk about what kind of requirements the substrates have. So for example, if we look at like tert-butyl chloride, if you remember when, so let's imagine like sodium hydroxide, so focusing on the hydroxide ion. Now in the previous lecture, we mentioned hydroxide is a strong nucleophile. And then of course we know from the last year of chemistry, hydroxide is a strong base as well. So it's both a strong nucleophile and a strong base. Now, if you have like a tert-butyl chloride or a tert-butyl bromide, that means that you have a good leaving group, but you know that this tertiary alkyl halide can't undergo SN2 substitution because there's too much steric bulk keeping the nucleophile away from the alpha carbon. So you cannot do a substitution reaction, an SN2 substitution reaction, I should say. However, you can actually do an elimination reaction, because for the elimination reaction, you're not reacting with the alpha carbon, which is sterically hindered. You're reacting with a neighboring beta carbon and the hydrogen that's coming off of that beta carbon. So this is much less sterically hindered. And so it's relatively easy for this hydroxide to actually pick off this proton and undergo an elimination reaction. Now, okay, so this is just like the first thing. This is just like kind of introducing you to this idea that basically SN2 and E2 reactions are going to be competing with one another for their substrates. And sometimes we're going to do a reaction and we're going to get a mixture of SN2 products and E2 products. Now, by the end of this chapter, we'll have covered all of that, basically like showing you, we'll give you like a nice chart and it'll be like, okay, if you have, in this case, we have a tertiary alkyl halide, it's reacting with a strong nucleophile and a strong base. What happens? Well, the SN2 product isn't seen, but the E2 product is seen in that case. There's, like I say, there's going to be a lot more messy scenarios here. We're just focusing on, for now, kind of the most obvious case, so we can kind of like show you one example of this competition. Okay, so now we produce an alkene, and if we're going to talk about alkenes, we probably better learn how to name them. So alkenes, remember, these are the, basically you just have a carbon-carbon double bond. And the good news is for alkenes, alkenes are named in a very similar way to alkanes. And so we just have like a few tweaks that we're going to add in when we name alkenes. I know you guys are really good at this nomenclature stuff. So we'll have a couple examples here, but I think you guys are going to get this no problem. So, okay, so the rules are basically, number one, you're going to identify the parent chain. No difference there, except for this parent chain has to include the carbon-carbon double bond. So that's the new rule. Your parent chain has to include the carbon-carbon double bond. Then you identify and name the substituents, no problem. Next up, you're going to number the parent chain, right? So now the only difference here is that the carbon-carbon double bond is going to determine which way you're going to number it. So in other words, you're going to number it on the parent chain, the side, starting from the side that's closer to the double-double bond. The double bond. Sorry, thinking about in and out. So just that basically, like, even if you have like a substituent on the complete other side of the molecule, you're always going to start from the side that's closer to the double bond. Then, of course, it's just the same thing. You're going to list the substituents before the parent name in alphabetical order. No difference there. Now, here is the big difference. Your parent chain name changes. Rather than being, let's say, pentane, let's say that we have an alkene, so a double bond that's starting from the first carbon to the second carbon. So we need to locate where that double bond is. And so the way that we're going to do that is we're going to take pentane, we turn it into pentene, so E-N-E rather than A-N-E. And then we give the number of the carbon where the double bond starts. So in this case, if it's between carbon 1 and 2, that means it's number 1. So there's two different ways we can name it. It can be 1-pentene, you may see that, and in simple cases, that's fine. But the way that we want to do it is we actually want to put that 1 in between the pent and the ene. So it becomes pent-1-ene. And just to be clear, it's like pent-1-ene. So we'll look at a few of these examples, and then we'll do a couple of them as well. So yeah, so just like I mentioned here, this is pentane, right? Becomes pentene, but this becomes pent-1-ene here. Now here you would say, okay, so like for example, with this one, this is an octane molecule, but if we change this to a double bond, well then we have to include the double bond there. So even though it's a shorter carbon chain, we have to include the double bonds. So that becomes heptene in that case. As I mentioned before, we're going to number it starting from the side that's closer to the double bond. So in this case, we could number it left to right. That's 1, 2, 3, 4, 5, 6, 7. Or right to left, 1, 2, 3, 4, 5, 6, 7. So even though your substituents are clustered on the right side of this molecule, because the alkene, the double bond, is on the left side, you're going to start from there. So this would be just to kind of like give a little more practice here. this is 7 carbons long, so it would be heptane. We know that becomes heptene, and then the double bond starts from carbon 2, so it's hept2ene. So yeah, this lists both of the possible ways that you can do it. Then you notice, okay, there's methyl groups on 2 of them on the 5th carbon and 1 on the 6th carbon. So that becomes 5, 5, 6 trimethyl dash 2 heptene, but that's not how we're going to do it. We want to do it this way down here, which is 5, 5, 6 dash trimethyl hept2ene. We want to get used to using this bottom method here. It might seem a little weird to kind of break it up that way, but we want to get used to using that method because in the future, next semester in particular, we're going to have things like enols. So it's basically like an alkene that contains an alcohol. And the way that we're going to name those is those are also going to come on the end here, where you could have, for example, hept2ene for all. So that way we can keep distinguishing between it's just going to help us in the future when we learn that. So just let's get used to learning it this way, where it's kind of splitting everything up here. Now, one other thing to remember, that there is a stereochemistry aspect that we talked about back in chapter 5, which is the EZ nomenclature. Remember, E is going to be where you have the substituents of the alkene on opposite sides of the double bond. So it's like this one is opposite this one. So that's the E configuration. So you just put E in parentheses in the beginning, just like what we did with S and R in the past. And this time it's like E or Z. So just keep that in mind. Now, if they were both on the same side of the double bond, then it would be Z. Okay, so yeah, sorry, I guess I could have skipped to this page. This is how we assign EZ, is we're going to use Kohn-Ingold Prelog rules, basically to give priority to both of these here. So let me show you like how I do this when I run into one of these problems. So like basically split the alkene into 2 halves, right? You've got vinyl carbon 1 and vinyl carbon 2. So we're just going to split it. Oh, geez. We're going to split it right in half like this. Then we're going to assign a 1 and a 2 to both sides, right? So fluorine versus an ethyl group. Well, fluorine is a higher atomic number, so that gets number 1. And then ethyl group is going to be number 2. Over here, it's hydrogen versus nitrogen. Of course, hydrogen is the lowest atomic number, so that's always going to be number 2. And then nitrogen is number 1. So then what you want to do, just go ahead and connect the number 1s. So just like draw a line in between them like this. Okay, well now in this case, the number 1s are both on the same side of the double bond, right? It's clear they're below the double bond in the way that we've drawn it here. And when I draw this line between it, this line does not cross over the double bond. So clearly this is the Z nomenclature because they're on the same side, remember? Like that's the funny joke we get to do each time we do this. So real quick, doing it over here, just to kind of like back it up. If we were, obviously the hydrogens here are going to be the lower priority. So draw a line between the main priority over here. That this time it crosses the double bond there. So this is the E configuration. So I hope that kind of makes sense as you kind of look at it. Yeah, so again, if the top priority groups are cis, they're on the same side, that's Z. If they're trans, that's E. So just keep that in mind. It's another way to think about it. Okay, so let's go ahead, give it a try. Give me an IUPAC name for these compounds, work it through, and you know, I'll do the first one with you live, and then we'll look at the names for the other 2, and let's try to figure it out that way. So okay, so let's start with the left one over here. So let's go ahead. Now we've got an alkene, obviously, right? And we want to find the longest carbon chain that contains the double bond. So it's going to be 1, 2, 3, 4, 5, and 6. We could go up there as well, but it doesn't really matter. So clearly that's going to be hexene. Then also we have to number it, right? So clearly the double bond is on this side. So this is going to be carbon 1 over here. This is going to be carbon 6 down here. So, oops, lost it here. There we go. So this has got to be hex 1-ene. So hex dash 1-ene. Okay, so next up we look for any substituents that we have, and sure enough, we have We have a methyl group on carbon 5. So then we just add that in. It's 5-methyl hex 1E. So just like that, that's all you got to do. I know what you're saying. It's like, oh, wait, what about EZ? Remember, EZ is only going to be when you have different priority groups on your alkene. So, but if we kind of look at it here, let me go ahead and draw this in here. Remember, these are both hydrogens over here. So which one's the number one priority? Well, they're both the same, and so they're symmetrical. The other way you can do this is by doing basically the same kind of test you do with stereoisomers, so like SR configuration. What would happen if you, so this is a hydrogen down here, right? What would happen if you flipped these two groups here? Do you create a new molecule? Think about it for a second. So flip them. Well, no, because you can rotate it in that case, and you would rotate it, it would be superimposable, so that would be the same molecule. So there's no E or Z notation to worry about in this case. Now these other two, there might be, so I'll let you go ahead. I'm gonna pause the video here. I recommend you pause your video, and when we come back, I'll have the answers. We'll just go over the answers real quick in that case. So we're back. In the second one here, we counted up 1, 2, 3, 4, 5 carbons. We're going to number it from the left side here because that is closer to the start of this double bond here. So it's going to be pent 2-ene. And then that means we have a methyl group on the 4 position here. So that is E 4 methyl, or I'm sorry, 4 methyl pent 2-ene. And then checking your, let's just like go ahead and check and see, connecting the dots here from this main priority group to this main priority group here. We cross the double bond, so that's E 4 methyl pent 2-ene. Over on this side now, it's 1, 2, 3, 4, 5, 6 carbons in a chain, so it's going to be hexene. Now we could number it either way. Either way, we get hex 3-ene. And then we see we have methyl groups on carbons 3 and 4. So 3, 4, dimethyl hex 3-ene. And then do this little test here. Clearly the ethyl groups take priority over the methyl groups. There's more carbons there. So in this case, they're both on the same side of the double bond. We don't cross the double bond, in other words. So it is a Z 3,4 dimethyl hex 3-ene. Okay, let me know if you have any questions on that nomenclature, because we'll have a bunch of these to do this chapter and next chapter. Okay, so really briefly, we mentioned alkane stability before. Now, we also have something with alkene stability, which is basically the fundamental principle is that cis isomers are going to be less stable than trans isomers. Now, the way you can kind of tell this is going to be, and I should say generally, so there are some like weird scenarios, but one thing to kind of like keep in mind is just draw a Newman projection and see how this works. So remember, for alkenes, these are sp2 carbons, right? So they're sp2, these are planar structures here. So if we were to take a look down, let's just like take a look down this axis versus a look down this axis here. And let me draw 2 different Newman projections here for us. So this is going to be for the trans, and this is going to be for the cis. Now, if you build your model for this, which I recommend you do, one thing you'll notice is with your double bonds, it's going to like constrain it so that these are all in the same plane. And what that means is your configuration looks eclipsed when you look at it through a Newman projection. So let's go ahead and draw it out here. So this one, the front carbon, CH3 up, like that. And then down, if we like kind of draw it out here, we're actually getting straight down. That's the hydrogen down here. Now we not only have that, we also have, the back carbon here. So the back carbon has a hydrogen up here. Let me just move these over. Sorry, I should have did this a little bit better, but I hope you can kind of tell the CH3 is on the front carbon, H is on the back carbon here. And so you have H eclipsed interaction or pseudo eclipsed interaction, as it were. And then For the back carbon down here, we have this methyl group in the back. So in both of these cases, we have the CH3 groups clashing with the hydrogen. Now in the cis case, hopefully you can see this, but and I'll just kind of draw the relevant one here. So it's going to be back here and back here, like that. As you can see, when we look at it from this angle, we have a CH3 group up top for the front carbon. And we have another CH3 group on up for the back carbon. So here we've got this like steric interaction where there's this big bulk of the methyl groups that are interacting with one another, and it's kind of pushing them away. Now I said earlier pseudo-eclipsed interactions. So the reason I just want to be clear that these aren't what we would call eclipsed interactions from when we studied Newman projections before and conformers of alkanes is that remember the bond angles are a little different. The bond angles for these are 120 degrees because they're sp2 carbons, whereas for the alkanes, remember those are sp3, so those are 109.5 degree bond angles. Okay, and we can again study this stability by looking at the heats of combustion. So like looking at that here, basically, the more stable a molecule is, the less energy you're going to get from the heat of combustion. So the trans alkene is worth is about 4 kilojoules per mole more stable than the cis alkene here. And even though this doesn't seem like a lot, that is enough to affect our reactions. And basically, remember, because these are more stable, that means that in cases where we have thermodynamic control of our reaction, the more stable product is going to be what we produce. So that's something to keep an eye out for. Now, each reaction has kind of like specifics for it, so don't take that as like the trans alkene is always produced. It's just something that we need to keep in mind as we move forward. Because some mechanisms are going to produce the cis reaction just because of the orientation of the reactants. So keep that in mind. Okay, so that's what we talk about cis versus trans alkenes. Now, another thing that we have to keep in mind for alkene stability is how many carbons are substituted onto the carbon-carbon pi bond. So the more alkyl groups you have substituted on the vinyl carbons, the more stable your alkene is going to be. So this is what we call a monosubstituted alkene. I'm just going to draw in the hydrogens here so that it kind of like makes it obvious here, right? So we have these hydrogens over here. Now, because these hydrogens don't involve any like large like antibonding orbitals, unlike these alkyl chains down here, these don't really do any hyperconjugation. If you want to remember what hyperconjugation is, just look at the last chapter. We had like a brief talk about it. It's basically where you have an antibonding orbital overlap with a pi orbital, and it basically stabilizes the pi electrons a little bit. So the more methyl groups you put on here, so here we have only one alkyl group. Here there's 2 alkyl groups, that's what we call disubstituted, 3 alkyl groups, that's trisubstituted, and then finally 4 alkyl groups, that's tetrasubstituted. The tetrasubstituted is going to be the most stable out of any of these because it can hyperconjugate with 4 different alkyl chains, whereas this can only do that with 3 chains, this can only do that with 2, and this can only do that with 1. So yeah, so that is just something to keep in mind about the stability of alkenes. Okay, now, so talking briefly about cycloalkenes. So cycloalkenes, if you have a cyclic alkene with less than 7 carbons, it has to have just the cis configuration. There's no trans cyclohexene, for example. Now, can you imagine why that would be? I recommend pause the video, think about what it would be. So try to imagine basically cyclohexene. It's just a bond angle thing. Like a trans cyclohexene would have to, you have basically like this molecule here. So this is 1, 2, 3, 4 carbons. So you have 2 carbons to get from 4 to 5, to get from 1 to 4, and it just does not fit. So you cannot fit a trans alkene into any of these with less than 7 carbons in the ring. So just so you know, like if you have cyclopropene, cyclobutene, pentene, or hexene, it's always got to be cis. You don't have to worry about that. Now, bicycloalkenes, we don't really talk about this too much. It's what's called Brett's rule. Basically just says that like you can't have a bridged bicycloalkene unless one of the rings is bigger than 8 carbons. So just keep that in mind. So down here, it's like you look at this and here this ring is 1, 2, 3, 4, 5, 6 carbons. And you could count the other one, 1, 2, 3, 4, 5 carbons. Neither of those is big enough. Again, you have to have 8 carbons in order to contain an alkene. So this compound is not going to be stable. You're not going to be able to isolate this compound. On the other hand, this one down here, 1, 2, 3, 4, 5, 6, 7, 8 carbons in one of the rings. So this compound can exist. It can be stable. It's kind of like this is kind of a minor point. Don't worry too much about this one. Okay, great. All right. So now E2 reactions. We've figured out alkenes. We figured out how they're stable and how to name them. Now let's get back to the E2 mechanism and basically what we call regioselectivity. Like how do we know which beta carbon is going to be deprotonated by a strong base? So let's just do like a sample example here. So let's take our tertiary carbon, but we don't have just all methyl groups here. We also have an ethyl group here. So then we have 2 different types of protons, beta protons, right? So remember, it's always useful. Just remember, this is our alpha carbon here. So we have beta carbons here and here. And these beta carbons are 2 different positions because this is a secondary carbon, right? It's bonded to 2 other carbons. And this is a primary carbon. It's like a methyl group, right? It's only bonded to the alpha carbon here. So that's going to be, those are different places. So, okay, so this means that the base here, NaOET, can go one of 2 ways, right? It can deprotonate the less substituted beta hydrogen, or it can deprotonate, and I'll draw this with a different color just to kind of like call it out here, the more substituted hydrogen here. Okay, so now if it deprotonates the more substituted product, that would give you this one here, right? So this is basically forming a new pi bond here. And so that gives you, this is what we're going to call the Zaitsev product. We'll talk about what that means in a second. Now, if it deprotonates the more substituted product, or the less substituted hydrogen, beta hydrogen, excuse me, that's going to clearly produce a different type of pi bond here. This is what we call the Hofmann product here. Okay, so to determine which one's the Zaitsev and which one's the Hofmann product, basically, okay, so I mentioned, right, so deprotonating the more substituted carbon, beta carbon, gives you the Zaitsev. Deprotonating the less substituted carbon, beta carbon, gives you the Hofmann product. So Zaitsev, more substituted beta carbon, and the Hofmann, that's from the less substituted beta carbon. Okay. Now, if we just use a small base like ethoxide, so ethoxide, let's talk about this. We're going to say this word a lot today. So ethoxide is the conjugate base of ethanol. So ethanol, just an ethyl alcohol, looks like this, right? So we deprotonate it. That gives us this guy here, ethoxide. So let's just kind of keep that in mind. That's our ethoxide. Now, the important thing to note about this is that this ethoxide is a relatively small base. So it's not a bulky base. That's going to be kind of the key distinction here. And it's a very strong base. It's a formal negative charge oxygen. So this formal negative charge oxygen is really going to grab the proton here. So strong base and not bulky. So when we use a not bulky base, we're going to form the more stable Zaitsev product preferentially. Now, not specifically, it's only going to form the Zaitsev product, but preferentially it's going to form the Zaitsev product. And that's because the Zaitsev product is more thermodynamically stable. So thermodynamically, we have a tri-substituted alkene here versus a di-substituted alkene here. The tri-substituted alkene is going to be more stable than the di-substituted alkene. So we're going to get like a 2/3 to 1/3 ratio here, or 70 to 30 ratio in this case. Now, so this is what we call regioselectivity. It's not regiospecific. It doesn't only react with the more substituted beta hydrogen. Instead, it reacts preferentially with the more substituted beta carbon. So now the thing is, we can actually control this regioselectivity by changing up the base. So let's say that, like, sometimes we're doing a reaction, like, and this is something that we're going to focus on for the rest of the semester. We're doing a reaction and we're getting to the point we want the Hofmann product of this. We don't want the Zaitsev product. So if we were to use sodium ethoxide as our strong base, we get a lot of the Zaitsev product that's worthless to us. We want the Hofmann product. So we can actually control that by using what's called a bulky base. So a bulky, sterically hindered base is going to favor forming the Hofmann product instead. So let's think about why that might be. So ethoxide, we already looked at it in this case. We've got 71% Zaitsev versus 29% Hofmann. If we change that base to tert butoxide, which is just the, that's this one here, that is the conjugate base of tert butanol, this giant bulky base all of a sudden is going to favor the formation of the Hofmann product rather than the Zaitsev product. And there's even bulkier bases that exist that will push it even further towards the Hofmann product. So this is a way that we can preferentially make the Hofmann product rather than the Zaitsev product. So here's your kind of like big split. Okay, so this is one of the first big splits in what we want to do, thinking strategically about the E2 reaction, which is, do you want the Zaitsev product, the more substituted alkene, or the Hofmann product, the less substituted alkene? To get the more substituted Zaitsev product, you're going to use a small, strong base. So something like ethoxide. Hydroxide could also theoretically work. It's just that it doesn't really dissolve in organic solvents. So we use ethoxide mostly. Do you want the Hofmann product? Well, then you need a bigger, bulkier base like tert butoxide. So this is often written, just so you know, like there's a couple different ways to write this. So you may see it a few different ways. So I'll just like write this now. This is sometimes written as OTBU minus or TBUO minus. You'll see it both ways as you kind of like study that, just so you know that's tert butoxide, and it's this big bulky base here. Okay, so there's a couple other ones that you'll see here. It's not just tert butoxide that's a big bulky base. There's also diisopropylamine and triethylamine that both represent these really big bases, and they're going to form the Hofmann product preferentially. So yeah, so just so you know, these are going to come up again because these tend to be non-nucleophilic, because the lone pair in this case is going to be kind of like sterically pushed away. Like it's not going to be able to act as a nucleophile very effectively, but usually it can grab a proton. So it's basic, but not particularly nucleophilic. As you can imagine, that's going to come in handy when we want to do E2 reactions or elimination reactions rather than nucleophilic substitution reactions. Okay, that was a lot of talking. Let's go ahead and predict the products here for a series of these. I'm going to work with you through the first one here, and then for the second and third, just like what we did last time, I'll ask you to like pause the video, work it out, and then we'll go over what the answer is going to be. So here it's predict the major and minor products for the following E2 reaction. So the first one is we have this cyclohexane molecule, and it's an alkyl halide, right? So it's cycloalkyl halide. So in order to start here, what we want to do is identify all of the beta carbons and then identify any of the beta carbons that have hydrogens. So first off, this chlorine is bonded to this carbon. That's our alpha carbon. Okay, then there's a methyl group off of this. That's going to be a beta carbon. There's continuing on down the chain, then there's two other ways down the chain. There's to the right and then to the left. Okay, so now let's go ahead and look for any hydrogens that we have here. So this is a CH2 here on the chain, so we definitely have a beta hydrogen here. This is a methyl group, so there's a hydrogen here as well. Okay, what about on the left side of the chain? Does this carbon have any hydrogens bonded to it? Well, count it up, right? It's 1, 2, 3, 4 carbons bound to the central carbon. So there's no hydrogens on there. So we cannot do an elimination reaction on the left-hand side. So that's good. That makes it easier, right? That means that our elimination reaction can be from this methyl beta carbon or this in the ring carbon. So let's go ahead. Let's just draw the mechanism. It's always good to kind of get practice with that. So I'm going to deprotonate this guy here. We're going to form a new pi bond between the alpha and the beta carbon. The chlorine leaves. And so that gives us a cyclohexene. The methyl group is still on this one, and we have 1, 2 methyl groups on this one here. Our new pi bond is right here, and the chlorine has left as a chloride. So I think I got all of that. Okay, so that's product number 1. And then product number 2, I'm going to use a different color this time to kind of hope that this can be kind of clear. I know it's difficult to see sometimes. So this one, we're going to the other beta hydrogen, deprotonated up here. We form a new carbon-carbon pi bond between the alpha and beta carbons. And once again, the chlorine leaves as a chloride. So my other product is going to look like this. Okay, so the methyl groups remain over here. Now, what was a methyl group is now an alkene that's pointed up here. Oops. Whoa. Okay, let me try one more time on that one. There we go. Okay. Let's try to draw a straight line here. There you go. Okay. All right. So this is our new kind of alkene up here. All right. Now, what I want you to do is identify the Zaitsev and the Hofmann product. So over here, ask yourself, what's the substitution on this alkene? What's the substitution on this alkene? This alkene is 1, 2, 3 tri-substituted. This alkene is 1, 2 di-substituted. The tri-substituted is more stable than the di-substituted. So this is going to be the Zaitsev product. And this di-substituted then becomes the Hofmann product. Sorry, I always get the Hofmann spelled wrong, so apologies for that. I know I just saw it on the last slide, but I screwed it up already. What that means is now, which one's going to be favored here? Well, we have to go back to which base we chose, right? We used ethoxide as our base. That's a small, strong base. So that small, strong base isn't sterically hindered. That means the more thermodynamically Zaitsev product is going to be major, more thermodynamically stable. And then the less thermodynamically stable Hofmann product is going to be the minor product. Okay, so go ahead and do that. We have the same molecule down here. So you're only going to get 2 different possibilities here, but 2 different bases used. So go ahead and try to identify the major products of those. So go ahead, pause the video. And when we come back, we'll have the answer. All right, so we're back. Both of these cases, we have an alkyl halide reacting with a strong base. So we get the same types of products, so the same structures here. The Zaitsev is the more substituted, where we've deprotonated the secondary beta carbon. The Hofmann is the less substituted, where we've deprotonated this primary beta carbon here. So the major difference here is the choice of base. If we use sodium hydroxide, that's a small, strong base, so the Zaitsev is going to be the major product. However, on the bottom, we use tert-butoxide. Tert-butoxide is a big, bulky base, so it can't get very close very easily to the secondary carbon, so it's going to pick off the primary carbon up here. So in this case, the Hofmann product would be favored. Okay. All right, so keep in mind, so let's take a look here. And let's talk about very briefly stereoselectivity in E2 reactions. So here we have dehydrohalogenation reaction, so that's the elimination E2 reaction, and we have 2 possible stereoisomers from that product. So in this case, it's 3-bromopentane that we're starting with. And when we dehydrohalogenate it, it undergoes elimination reaction. We can form either a trans product or a cis product like this. Now, in this case, as you can imagine, the trans product is going to be more stable, which is what we just talked about, And so it's going to be preferred as the product thermodynamically over the less stable cis product. So like imagine basically like why is it that the trans isomer is going to be favored? Well, in this case, we're looking at the energy diagrams. Not only is the trans product more stable, the activation energy is less as well. So it'll be kinetically and thermodynamically favored. Okay, now here's the thing. We're going to talk about the sterics of this. So I recommend go ahead, build a model of this molecule here. Now you don't need to draw, like put in a full phenyl ring here. Just have like a red one over here, and you can have, make this like black, red, green, and black again here. And we're going to look at this as we form it here. So I'm going to get my my model out, and we'll go over this in just a second. All right, I'm back with my little model here. Hopefully you had some chance to make yours. Like I mentioned, just I recommend replacing the phenyl group with a red one. Just you don't have to build a big one here. And then on the second carbon, the tert-butyl group, that can just be a black one, like as a placeholder, basically. So I've set mine up so that it should look correct to you as you see it here. The red, the phenyl sticking out at you, black methyl on this side, and then hydrogen pointing down on the left side. And then the right side is the bromine, the hydrogen pointing out at you, and the carbon pointing in at me. Okay, so you would think that perhaps like you could form either isomer like E or Z isomer with the elimination, and based on what I've told you so far, that would be the case. However, as it turns out, only the E isomer is ever formed from this particular reaction. And the reason for that is because the 4 atoms basically that are involved in the mechanism, which is the beta hydrogen, the 2 carbons that are going to form the new pi bond, and then the leaving group, right, the bromine in this case, they have to be in the same plane. So practically speaking, there's only 2 ways that you can do that. You can have this configuration where they are in the same plane, they're anti to one another like that, or they're syn to one another, in other words, they're in the same plane this way. But as we know, this right here, that's an eclipse conformation, right? And an eclipse conformation is very unstable. So that can only happen like momentarily. The staggered conformation, where they're anti each other, the bromine and the hydrogen here, that's much more likely. And as it turns out, that is exactly the conformation that's going to be the active conformation in an E2 reaction. So what we say is the beta hydrogen and the leaving group have to be coplanar or periplanar. So that just like, we'll talk about what that means here in a second, but this is exactly what I just showed you here, where you can imagine either having them anti like this or syn like this. Those are the only 2 possible active conformations, but anti-coplanar is staggered, and so it's more stable than the syn coplanar, which is eclipsed, excuse me. Right, so this is a high energy rotamer. This isn't going to happen. The low energy rotamer, that is possible. Now, when you do that, check it out. So let me draw this in here real quick. So we have our base come in. It's going to deprotonate the proton here. And we're going to form a new pi bond between the back and the front carbon. I know you can't really see that, but I'm doing my best. And then the bromine is going to leave on the other end. So as you can see here, there's only one possible way for this to go. The methyl is going to be on the left and the phenyl on the right. They're just going to go like that. Because otherwise they'd have to like rotate around entirely. That can't happen in your transition state here. So you're always going to end up with the methyl on the right, the phenyl on the left, and the T-butyl on the left, and the hydrogen on the right in the back carbon. So go ahead, play around with that, play around with your model a little bit and see if that makes sense to you. But basically, this is always going to be the active conformation where it's anti-coplanar. Now, I said earlier something about periplanar. So coplanar, that makes sense, right? It's atoms that share a plane. But as it turns out, it doesn't have to be exactly a 180-degree dihedral angle. 175 to 179 dihedral angles will work as well. That's enough overlap that you can make it through the E2 mechanism. So the more correct term is anti-periplanar, so that you can have a little deviation there, like if there's a particularly bulky group. So sometimes, because of this anti-periplanar requirement, you actually are going to form the less stable Z isomer, just because that's the only thing that's possible. So go ahead, let's try to do that here, where you're forming your new products here. I'll do the top one and you can do the bottom one here. So I recommend just go ahead and draw in the mechanism, right? So you're going to deprotonate the beta proton, form a new pi bond between the two carbons, and you lose your bromide. Okay, I'm just going to draw it out like this, and then we'll kind of write in what we have up here. So now I always imagine myself looking down on this from the top. And when I look down on this from the top, I see that R2 on the left carbon is going to be up because that's going into the plane like that. R1 is going to be down. That's coming out of the plane here towards us. And then over here, same deal. R2 is going to be up. This is going to move up this way. R1 is going to move up this way. So R1 is going to be on the bottom and R2 is going to be on the top. Do you see why that, do you see how that works or why that makes sense? This is another easy way to draw the anti-coplanar structure in non-Newman projection form, because here the hydrogen, the two carbons, and the bromine are all on the same plane because you've rotated them such that they are, they're not the dashed or the bold wedges here. Now do the same thing down here. Give it a shot. So pause the video, come up with your product, and then we'll do it together. Okay, so down here, we deprotonate again the beta hydrogen, form our new carbon-carbon pi bond, lose the bromine. That gives us an alkene. Like that, like that. This time, as I look from the top down, again, I'm imagining myself looking this way, so I go into the screen. I see that R2 is up here, R1 is down here, and then over here, R1, which was going into the screen, is on the top, and then R2, which is coming out of the screen, coming out towards me. So there you go. That's how you can determine what the product is going to be. Yeah, so if you, so now in this case, this one here, we have two different beta hydrogens. So there's two different rotamers that are possible. And in this case, so you will get a mixture of the two possible products, because depending on which way this is rotated, basically, if you look at the Newman projection, it'll tell you, oh, it's going to be on the top or it's going to be on the bottom. So basically, you're only going to, it may be selective in one case. In other words, if you have one rotamer that's higher energy than the other due to Gauche interactions or something like that, it's going to select the one that's more stable to react with. It's more likely to react with that one, but you're still going to get a mix of the two products. Again, it's only going to be stereospecific when both alpha and beta are stereocenters, like what we saw in the previous example. Now, okay, so it's important at this point to define stereospecific versus stereoselective. So stereoselectivity is where you take your reaction, so you have your reagent and whatever base or whatever you happen to use, and that reacts to form a major and a minor product. So it might be something like 80% the major product, 20% the minor, or it could even just be 60% the major and 40% the minor product. So keep that in mind. It's selective for the major product. In other words, it's preferred to go to the major product, but it's not impossible to make the minor product. Stereospecificity, well, think about that word specific. That means the reaction can only produce one product, and it is stereospecific. It's only going to produce one of them. So just keep that in mind. Stereoselective, you get an abundance of one over the other. Stereospecific, you only get one and zero of the other. So for example, with E2 reactions and cyclohexanes, this is going to be something that you're going to see again and again. So I strongly recommend paying attention here. When you have a dehydrohalogenation reaction, that's the E2 reaction of a cyclohexane derivative, the leaving group and the beta hydrogen, remember, have to be anti-periplanar, right? So in the equatorial position here, when chlorine's in the equatorial position, its anti group is the other cyclohexane, the other part of the cyclohexane ring. So elimination can't occur on this side. Now, when it's axial, it's pointed directly up. The beta hydrogen is anti, it's pointed directly down. So in this case, it is anti-periplanar, so the E2 elimination can proceed. So just keep in mind that when you look at cyclohexanes, sometimes you're going to have eliminations that cannot occur. And so that's a good trick question that I'm going to pull on you from now on. Just keep that in mind. So here, so give this a thought. Which of the two molecules will not be able to undergo an E2 elimination reaction and why? Keep in mind, you may want to draw the chair structures to help you figure this one out. So I'll give you a chance to stop to think about it. I will pause the recording, and when we pick it back up, I will explain the answer to you. So go ahead, pause it. So looking at these Newman projections to help us figure it out, on the right here, what we notice is the chlorine, when it's in the axial position, it's going to have a methyl group anti to it in the axial position. So that means that in no case can this hydrogen actually be anti-coplanar or anti-periplanar to this chlorine. So this one cannot do it. It just does not have the possibility of that. Now, on the other hand, here on the left structure, if you draw the chlorine in the axial position, which is going to have to be axial if it's even going to have anything anti-coplanar to it, then the front hydrogen here is actually pointed down, so it's anti to the chlorine. So that means now that the reaction can proceed. The elimination reaction can happen where you have your base attack the proton, you form your alkene here, and then the chlorine leaves. So this one is good. So that's your answer right there. So make sure to think about that. That's definitely going to be something you see on the test. Yeah, so like for example, let's take a look here at this reaction here. Here we have chlorine, basically a cyclohexane that's substituted with a tert-butyl group and a chlorine. And when you put in some sodium methoxide, you have a very slow E2 reaction. But if you have, and those are kind of opposite one another, right? These are trans, right? And then here, these are cis on the cyclohexane, so they're on the same side. And here, the E2 reaction is fast. Additionally, you only get one product on this reaction here, whereas on the second one, you actually get two possible products. Basically, here we get a Zaitsev product and a Hoffman product. So what would account for that difference? Why don't you think about it for a second, pause the recording. Why is it that you only get one product and you have a slow reaction here, whereas down here you have a fast reaction and you get two different products? So the reason that we get two different products down here is versus one product up here is going back to what we saw before. We know that in this case, this hydrogen is poking down here. If the chlorine and the beta hydrogen are both cis to each other on this cyclohexane, then they're never going to be coplanar. They can't be coplanar, and so they can't form that they cannot form their anticoplanar relationship that they need in order to go into the transition state to be active for E2 elimination. So that can't happen. Now you can get this one over here where you have an H down, an H up, and an H down. But you form a thermodynamically less stable di-substituted product, whereas down here, we have our E2 reaction occur fast because here, the chlorine and the hydrogen are trans to each other. So these can form a anti-coplanar relationship, and that would form this product right here, a more stable tri-substituted alkene. If you don't believe me, go ahead, draw your Newman structures, Newman projections, and you should be able to see it for yourself then. Okay, so basically there's a lot of things to consider, right? This was a very long lecture, longer than I thought it was going to be, but that's okay. So there's a few different things you have to consider whenever you're doing an E2 reaction, right? So you have to ask yourself, is the substrate going to react stereospecifically? In other words, how many beta hydrogens are there? And so stereoselectively is like how many different beta carbons are there, and do those beta carbons have hydrogens? And then is it stereospecific? In other words, are the neighboring carbons, are they chiral? In which case you're going to have a stereospecific reaction. Are there going to be regioisomeric alkenes? Like that's where we have the Zaitsev and the Hoffman product. And if so, what's your major product? given steric hindrance of the bases that's used. In other words, the strong bases are going to produce the more substituted product, the Zaitsev product, and the bulky big bases are going to produce the less substituted Hoffman product. So it's a lot of practice basically to do that. So we got a bunch of practice in the book. I have more practice posted down below in the discussion. Make sure to ask questions, and I will see you guys soon. All right. So that'll do it for now. We'll talk about E1 and SN1 reactions in the next lecture.